This is our last video for Chapter 4, and we're going to work on the quantum mechanical model and electron configurations. So this video will be a little bit longer, but I wanted to put all the ideas together in the same video, so it's a little bit longer than I try to usually make. I like to include this illustration with many of the videos I have from Chapter 4 because I like how it shows the progression of the models of the atom. So we've already talked about Dalton, Thomson, and Rutherford. Rutherford was where we get the nuclear model. So we have a center of the atom, and we know now we put the protons and neutrons in the nucleus, and then the electrons are outside the nucleus. It was Bohr's model that started to think about how the electrons were outside the nucleus, and his model is here almost at the end here, Bohr's model. And he had this kind of planetary model where you had the nucleus and then the electrons orbited in specific energy values, what we call quantized energy levels, around the nucleus. And Bohr's model worked very well for the hydrogen atom, which has only one electron. But in the progression of starting to look at helium and other elements, this model would not predict or match what we saw for other elements. And so then comes in the quantum mechanical model. So you can see here is the quantum mechanical model. Now, quantum mechanics is based on mathematical solutions. We are not going to be looking at the math of the quantum mechanical model. I think of it like picking fruit. We're going to look at the concepts that we get from the quantum mechanical model that allow us to think about the electron placement, what we call electron configurations, and how that can help us predict ions and bonding. So there'll be some things in here that you might scratch your head on because it's very theoretical, and but you can get it. So let's jump in to how we're going to approach the quantum mechanical model in introductory chemistry. So with Bohr's model, he treated the electron like a little particle that was orbiting the nucleus. And we saw that it made great strides in the contribution to how we understand electrons, especially when we think about the energy being quantized. It was not a model that could be applied to things outside of the hydrogen atom. Well, in the early 1900s, but after Bohr, which was, I think, maybe 1911, 1913, you don't have to memorize the dates. Just I like to think of the progression. De Broglie, a French physicist, you see here, he proposed this sentence right here. That matter wasn't just treated like a particle, like a substance, but it could also be treated like a wave. Now remember, in Bohr's model, we talked a little bit about waves and how energy, like visible light, can travel through space in waves. So this idea that matter could be treated like a wave or like a particle was new. And if you read through on this slide with me, there. So the idea was that when you have large objects, things with large mass, the wave properties of that object are negligible. Remember from a previous video, negligible means that it is not important or does not have an impact. So because you have a large mass and small wavelengths, in larger objects, we don't really see the wave properties of that matter. But when you have smaller objects, like an electron, which has a very small mass, like 10 to the negative 28 grams, then the wave-like properties of that form of matter will have more impact. fact. So it becomes more important. So with this idea, Schrodinger, you can see here, so in 26, so these thoughts are happening around the same time, decided he wrote mathematical equations that explained the electron behavior using what we call wave functions. So he described used equations to describe the electrons as waves. So in this theory, quantum mechanics, what happens is instead of calculating the exact position of electrons, the calculation involves calculating the highest probability of finding an electron in certain regions. So in quantum mechanics, it doesn't allow you to calculate an exact location of electron. Instead, you calculate the probability of finding the electron. And so the idea that an electron has not just particle-like properties, but wave-like properties was the foundation or one of the thought processes in quantum mechanics. So these wave functions and the solutions of the mathematics and quantum mechanics gives us something called quantum numbers. And there are 4 quantum numbers for each electron, and that describes the location of the electron. Well, the highest probability. Remember, it's probability, and we'll see as we go. We're not calculating probabilities, so my statistics people and things, don't freak out. We're not. Okay, so there's going to be, maybe I'll put up here 4 quantum numbers. So these are the solutions, and what we're going to look at are these solutions. And what you're going to see, which is super cool about these solutions, is they apply directly to the periodic table. So we will be able to, once we start working with how are we, identifying the probability of where the electrons are, we're just going to look at the periodic table. It's very cool. So here again, just to reiterate, in quantum mechanics, we are dealing with electron probabilities. So no longer are there orbits. I'll just cross that out as an emphasis. So there were the electrons not orbiting. Instead, we call these regions of probability orbitals. So they are going to use the word orbitals. So when we see orbitals, these are the regions of space with the high probability of finding an electron. And here is an example. If you plotted out where the electron could be, what it might look like. Now, we're not going to be drawing things like this, but it's kind of a visual. So the darker the region, the higher the probability of finding an electron. So orbitals are described as regions of high probability of finding the electron. So let's look at the quantum numbers that and the funny thing is they're not going to be labeled as numbers. They're actually labeled as letters for us, but they're called quantum numbers. Let's look at how they're defined, how they apply to the periodic table, and how they tell us where electrons are. So the first quantum number tells us how far away the electron is from the nucleus. It's something called an energy level. Okay, so it tells us how far away the electron is from the nucleus. So you can see right here. Principal energy level. It's a general idea of the distance of an electron from the nucleus. Okay, these numbers start at 1 and go 1, 2, 3, 4, 5, 6. If you're looking at this picture here, it's trying to just give an image of what it's talking about. Do you see energy is here, and as you go higher, it goes up. And then the lowest one would have a quantum number of 1. So that's the lowest energy level of the electron. It would be closest to the nucleus. And then they get farther and farther away, higher numbers. And notice they're not equidistant. Mathematically, they actually get closer and closer and closer, and eventually it would be like an infinite thing where they would look to our eyes like they're almost right on top of each other. Now, this idea of principal energy levels does overlap or complement the idea that Bohr had of quantized energy levels. Because remember, his were equal, these orbitals. The electron was orbiting the nucleus. I don't think they were equal either, but they were orbiting the nucleus. And so this is a similar idea that the electron can't be any particular place. It's quantized. It can only be in one of these certain energy levels. So our first quantum number is called the principal energy level. You can think of it just as the energy level, and it will start with the number 1, and the farther away you get from the nucleus, it has a higher number, and it just goes numerically, sequentially, like 1, 2, 3, 4, 5. So that's one quantum number. Now, each energy level has sub-levels, one or more. So it's not going to be equal, not going to be the same for each one. If I'm looking at the language here, the word sub means like below. So I always think, okay, a sub-level is something below or inside the level. So you have an energy level, which we know is a 1, 2, 3, 4, 5, 6, 7. And then inside the energy level, there's something called a sub-level. So you see here, energy levels are divided into sub-levels. The sub-levels will correspond to different types of orbitals. Remember, orbitals are regions of high probability. And that's where the electrons will be. So it's like you have an energy level, and now we're going to have another place inside there called a sub-level. Inside the sub-level is going to be the orbital, if we're kind of trying to piece it together. Now, if you're already starting to scratch your head and thinking, what? Levels, sub-levels, orbitals? I encourage you to try to watch the video to the end and see how we put it together on the periodic table. And then perhaps, if you have time, I would encourage you to re-watch this part, because once you get to the end and see how it's connected, the beginning may make more sense. So this is something that kind of has to simmer a little bit. Okay, so we're going to take our energy level, divide it into sub-levels, and here's going to be an important takeaway in red. The sub-levels are going to be given letters, and there's only 4 different letters they can have: S, P, D, and F. Now, these letters represent different words, but those words I don't think you have to memorize. I included them here on the slide: the sharp, principal, diffuse, and fine. It was just how, when people were investigating it, that they identified things. We don't have to know those words, but we do need to know S, P, D, and F. Now, each energy level, think of it like layers. Sometimes people think of it like a building, like floors on a building. So you'd have like the first floor, then the second floor, then the third floor. Each floor or level is going to have some sub-levels, and the number of sub-levels it can hold is equal to the energy levels number. So I said that in words. Let's look at it on this chart. So here's the energy levels. Right there. 1, 2, 3, 4. It can keep going. These are just 4 common. And notice, so 1 has 1 sublevel inside of it. 2 has 2 sublevels. This is what the line is saying, what the last bullet point is saying. The number of sublevels in an energy level is equal to the N value. That's the energy level. That's what N is. 3 would have 3 sublevels. Sorry, the writing is so messy. 4 would have 4 sublevels. Now, there's only SPDF, so even if we went to 5, we could only have 4 sublevels because there's nothing more than SPDF for us. So then if we now take that idea and we look over to this side, so 1 only has an S. Energy level 2 has an S and a P. 3 has 3 of them, S, P, D, and 4 has all 4. So depending on the energy level, that's how many sublevels you will have. Now, it will make sense if you think about it, and I know the what I'm about to draw looks like the Bohr model. But it helps, what I'm really trying to show you is that as you go farther away from the nucleus, the radius gets larger. So the first level only holds 1 sublevels. The second level is bigger, so it can hold 2. The third level is even bigger, so it can hold 3. And the fourth level is even bigger because it's farther away from the nucleus, so it could hold 4. So like the first level can't hold 4 sublevels. It's too small. So if that helps you kind of think, why would it keep getting bigger? Well, the radius keeps getting bigger. The farther away you get, there's more space there. So, okay, so let's put it together. Our first number to describe where an electron is the energy level. And then inside each energy level are sublevels, okay? And I do have a slide that puts it all together, so hang in there. Now finally, so we have, I'm just going to write down at the bottom, we have the energy level. And inside and this is going to be numbers, 1, 2, 3, 4. Inside the energy level, we have sublevels. And these are S, P, D, F. And inside the sublevels, we finally have the regions of high probability. This is where the electrons are, in the orbitals. Now, here's a funny thing. The orbitals have the same letter. And how it works is, if you are in an S sublevel, you will only have S orbitals. If you are in a P sublevel, you would have P orbitals. If you are in a D sublevel, you would have D orbitals. And if you are in an F sublevel, you would have F orbitals. So the orbitals are named after what sublevel you are in. So let's look at the slide and some of the illustrations. And I expect you to know what an S and a P orbital would look like, but you don't have to know the D. I did not find an image for the Fs, but the Fs look very similar to Ds. They're not it's that kind of image. So let's take a look up here. It says, I'm looking at the top, each sublevel contains a different type of orbital. Okay, and here's what the definition of the orbital is. The orbital is where the highest probability of finding the electron. So orbitals are where the electrons are. Okay, that's where we're going to find them. Now, if you have an S sublevel, so S sublevel has 1 S orbital. Okay, so anytime you have S, this will only have 1 orbital. And it looks like this sphere. So any S looks like a sphere. Now, if you're on the first level, every level, I'm going to go back for a second and I'll come back here. But if you look, every level has an s orbital. I mean, every level has an s sublevel, which means every level has an s orbital. And how they're different is, if I was in the first level, my orbital, I'm going to try to draw something small. My orbital would be small. If I was in my s orbital, if I was in the second level, if I was an s in the second level, then my orbital would be a circle that was bigger. And if I was in the third level, but I was an s, my orbital would be even bigger. So more than one level can have an s orbital because all of the levels have an s sublevel. And how they're different, they're all the same shape, they're all a sphere, but the farther away you get from the nucleus, the bigger those spheres become. Now, I told you this is a lot of kind of theory. Don't give up on yourself. Look through this once, kind of see how it fits together. Look through it again. If you need to, go on to other videos. We just need the concepts of this, but it is a lot at first. It's not normally how we think about things. So, and I'm going back to the orbitals. An s or a sublevel has one s orbital. A p sublevel, remember there's s, p, and d. P's actually have 3 orbitals. Now, I always think about this in math. These are mathematical solutions of probability. And I think about, okay, so in some ways, in different types of algebra, you may be solving an equation and you will come to the end and find that there's actually 2 different numbers that will solve that particular equation, right? There's 2 answers that are correct. So I kind of apply that in a very broad sense to this. These are mathematical solutions. So in the p sublevel, when they're looking at p orbitals, there were 3 equal solutions to that mathematical problem. So if you have a p orbital, there's actually 3 possibilities. If you put them all together, they look like a flower. So you can see they've done colors. Each one by itself looks kind of like a dumbbell, like it comes together and where the nucleus would be, and then it has 2 big, what they call lobes, lobes. And so there's one on the x-axis, one on the y-axis, and one on the z-axis. And here they make the x-axis blue, the y-axis purple, and then the z-axis kind of that orange color. But those are 3 equal p orbitals. Okay, so let's go to the next one. So in the next one, we have a d sublevel, and mathematically that comes up with 5 different answers. So when you're in a d sublevel, you actually have 5 orbitals. They're all called d because the orbitals are the same. And you can see here, they did not overlap these. They wrote them all individually, but these would be the 5 solutions to the probability of the d orbitals. My favorite one, the one I could always remember, was this one. It looks kind of cool. And then finally, the F's, which is the last sublevel that we're going to be able to have. We have F, and it contains 7. So there were 7 answers. So at the beginning of this, I told you that there are 4 what we call quantum numbers. So 4 things we need to know to figure out the location of each individual electron, according to this theory. And so there's the energy level, which is numbers 1, 2, 3, 4. And then each energy level has sublevels, depending on which energy level, that are called S, P, D, and F. And then each sublevel contains orbitals, and the orbital letter is the same as whatever sublevel that you are in. And so those are 3 of the things we need to know. The 4th one, which is only important when we're doing, for us, box diagrams, which I haven't shown you, I'll show you later, is, oops, it looks like I had two of the same slides together. I'm going to take it off. Okay. The only one that the fourth one, sorry, I had that, threw me off because I put two of the same slide in. That has to do with what we call spin. And so every orbital, here's an important thing. This is very important. Any atomic orbital can hold 2 electrons. It doesn't matter what type. An s orbital can hold 2 electrons. A p orbital can hold 2 electrons. So s could hold 2 electrons. Any p could hold 2 electrons. Any d can hold 2 electrons. Any f can hold 2 electrons. Any atomic orbital holds a maximum of 2 electrons, and they have to have opposite spins. Sometimes this doesn't matter to us that they have opposite spins. We will be drawing some things with electrons, and in that case, how we show the spin is we draw an arrow up and an arrow down. So let me just go again, and let's think about what we have. And then I have a slide. We'll put it all together. So we have energy levels. And there's 1, 2, 3, 4. And something just popped into my head as a bit of reassurance for you. All of these numbers are going to go on, and letters are going to go on to the periodic table. And so we are going to be able to, and I'm going to show you how, look at the periodic table and, for example, know what energy level it is. Or we'll look at the periodic table and we'll know what sublevel it is. Remember then, inside sublevels are orbitals, and they have the same letters. But underneath, I'm going to write, if it's an S, there's only 1. P's can have up to 3. D's have 5, and S have 7. So the orbitals, they kind of branch out a little. And then we have spin. And spin will either be, they usually use plus or minus a half, but what they're saying is 1 is going to go up and 1 is going to go down. And only from the spin, what we have to remember is that 2 electrons in each orbital. Okay, you've got to remember that. The up and the down thing, when we do orbital box diagrams, I'll show you the up and down thing. Okay, so let's try to put we're going to start really piecing it together. So here's one thing that pieces it together. So the question is, how many electrons are in each sublevel? So let's look at this chart and see. Okay, so here are the sublevels. And remember, depending on the sublevel, that depends on how many orbitals you can have. Now, I am a super pattern person. Patterns help me remember something. And so I look at this pattern. I see counting by odd. So I go 1, 3, 5, 7. Sometimes students see, I add 2 to each one, which either one helps you get there. But it's a nice pattern. It's not jumping all around. So S only has 1 orbital, which would be called an S. The P has 3 p orbitals. The D sublevel has 5 d orbitals. And the F has 7. Now, from the previous slide, we know that each orbital can only have 2 electrons. So if you multiply the number of orbitals by 2, then you discover how many electrons can go in each sublevel. So the S sublevel can only have 2 electrons. P can have 6, D can have 10, and F can have 14. Now, again, I keep wanting to reassure you, I have a table that puts it all together with the letters and numbers I've been using. And then we're going to look at the periodic table, which you can't see my face, but I get so excited how this model, which it should, goes right onto the periodic table. And when we do our work, that's what we're going to use. Once you learn how the model fits on the periodic table, it makes things much easier. So this is a slide from your textbook that tries to put all the numbers and letters I have mentioned. And so let's kind of go through this together. So over here, I'll try on the far left of the table, let me get a lighter highlighter because I'm afraid it's covering the words too much. Here's the energy level. Okay, and remember they go down 1, 2, 3, 4. And the energy levels have sub-levels. Now, just as a reminder, then we'll look at the chart. Whatever number on energy level you are, that's how many sub-levels you have. So one energy level has one sub-level. The second energy level has 2 sub-levels. The third one has 3, and I'm running out of space. The fourth one has 4. Now, the sublevels are S, P, D, F, and they always start over every time you go to a new energy level. So the first one, if it only has 1, it would have an S. The second one would have an S and a P. The third one has S, P, D. The fourth one has S, P, D, and F. Okay, so it has 4. So let's look back at the chart. Okay, so here are the energy sublevels. And notice they write it, so there's 1S, and then there's 2S, 2P. So here's something we need to know and notice, that the number in front of the letter is the energy level. Okay, so if I have a 1S, this is energy level 1. And then that is the sublevel. So then if I have 2S, that is the energy level. And that is the sublevel. So it's not that there's 2 S's. That number in front is telling you what energy level you're in. Then in this table, they say how many electrons are in each sublevel. Well, we do have to remember, and I'm going to write it down here on the side for you, that an S has 1 orbital. So that's 2 electrons. Any P, whether it's a 2P, 3, there's no 1P, 2P, 3P, 4P, this has 3 orbitals. So that will always be 6 electrons. Any D sublevel has 5 orbitals. So that will be 10 electrons. And then F has 7 orbitals. So that will have 14 electrons. So when we look, like anything with an S has 2 electrons because they only have 1 orbital. Then if we keep looking, anything with a P has 6 electrons because they have 3 orbitals. Anything with a D has 10 because they have 5 orbitals. And then we have our F, which has 14. And if you went to level 5, which there is a level 5 has S, P, D, F. They would say 5S, 5P, 5D, 5F, but it would look like the 4th level, like it would have 2, 6, 10, and 14. But for the elements that we have, we only need 4 sublevels. So then looking at that, we can see how many electrons are in each energy level. So for example, the first level only has 2 electrons total. The second level has 8 electrons, 2 plus 6. The third level can fit 18 electrons. And then the fourth level can fit 32 total electrons. So this slide tries to put together the energy levels, the sublevels, which then contain the orbitals. Now, what is not here are the spin. Spin, what we just need to remember from that is that 2 electrons each for each orbital. The plus and minus spin, again, really only comes in play for us if we are writing orbital box diagrams, which I keep saying that word and I haven't shown you, but I will show you. So again, to try to encourage you with some of this quantum mechanical, which sometimes feels when you're first learning like learning it mumbo jumbo, we're going to look at the periodic table and see how this all fits. And then I really encourage you, after you've kind of gotten your head around that, to come back and see if you can't put it together again. The first time you hear this, it really does feel like a lot of mumbo jumbo, S's, D's, P's, F's, numbers 1, 3, 5, 7. Oh, everything only has 2. Like I can see how when you first hear it, it feels like a lot. But be patient with yourself. I would say look at the periodic table once we get there and then try to come back and see if it will make a little more sense. So I did make a few practice problems, and what I encourage you to do is to pause the video, read the question, try to answer it, and then I obviously am going to just keep talking, and so I will answer it for you, but test yourself, see if you're getting it, so that you can catch any misunderstandings or places where you need to keep working a little. All right, so you can pause. So it says, what is the maximum number of electrons in a 4D sublevel? Now I am going to go through the explaining part of it. So when I look at this maximum number of electrons, okay, the number 4 really doesn't matter to me to answer this. That does tell me that I am in energy level 4. That's the only one that could have a D of the ones that we've been working with so far. But what tells me how many electrons is the D sublevel? So my thought process would have to be a D sublevel D has 5 orbitals times each orbital has 2 electrons each. So this is going to be 10 electrons in any D sublevel. If it was a 5D, 6D, 7D, does not matter. D, it's the sublevel. So a D sublevel has 5 orbitals times 2 electrons. So if you answered letter D, you are correct. If you answered one of the others, hopefully the explanation would get you on the right track. If not, feel free to ask me a question. Okay, let's try another. Okay, you can pause if you want to try to answer it before I just go on. All right, what is the maximum number of electrons that can occupy the N equals 3 energy level? Okay, so this is what, I'm in the 3rd energy level. And this is what I think to myself. So the number of the energy level tells me how many sublevels. So the 3rd energy level would be S, P, and D sublevels. Now, then I have to think, okay, orbitals are what hold electrons. How many orbitals? So this has 1 orbital. P has 3 orbitals. D has 5 orbitals. And it doesn't matter what level I'm on, that is true about the sublevels. And then each each orbital, correction, has 2 electrons. So I have 2 electrons plus 6 electrons plus 10 electrons. So the third energy level has letter D, a total of 18 electrons. Now you might have just memorized 18. However, what I showed you would be the reasoning by how we got to 18. So that's how you get to 18. All right, so those were 2 examples. There's more in your homework. There's more in the textbook. Just kind of put things in front of you till you get it all squared away in your head. Now, I want to mention a special kind of valence electrons before we get to the periodic table. And these very special kinds, which are the most important for us in bonding, they're called the valence electrons. So the definition of valence electrons is right here. So valence electrons are the electrons in the highest energy level for that specific atom. So I think of them like here it says outermost or the outside. These would be the electrons on the outside of the atom. And so it makes sense that they would be involved in bonding because the outermost electrons from 2 atoms are the ones that are going to interact with each other. So valence electrons are the outermost, and the important part of them is that they are involved in bonding. And so you can see that is what this second and third bullet point say. Chemical properties, so how they react, is determined by the valence electrons. And then another way, valence electrons participate in bonding to form compounds. Well, that has also to do with reactions. Okay, so it's our valence electrons that have to do with chemical properties, chemical reactions. And so you'll see what's kind of cool, and we'll do a lab, elements that have the same number of valence electrons, and there are groups of elements that do, tend to have similar chemical properties because it's all driven by their valence electrons. Now, there's a really easy way to figure out valence electrons. If it's in the representative elements, which we will get to, the column number, what we call the groups, the number in front of the letter A tells us the valence electrons. So, for example, if you have 1A on the periodic table, this has 1 valence electron. If it was a 2A on the periodic table, it would have 2 valence electrons, etc. So this number here, the one that follows the A. And when I get to a periodic table, I will reiterate that. I don't have one on this slide, but when we get to it, I will explain with the periodic table as well. Excuse me. So this says how many valence electrons does phosphorus contain? Now, I'm kind of feeling mad at myself. Okay, here's the periodic table. I haven't gotten to any of this yet. I will, but let me show you what they're talking about. So here are the columns that we're talking about. They're called groups. And do you see how, and I think in the next chapter, in chapter 5, we're going to go into this even more. So this is kind of an introduction. But do you see how they have numbers followed by a letter right there? So the question was, let me go back. How many valence electrons does phosphorus contain? Now, if you have a periodic table with what I just showed you, you can go and see if you can figure it out. I'll go ahead and answer it here. So I got to find phosphorus. Okay, so phosphorus is right here. It's element 15. And if you go up to the periodic table, do you see the number 5? phosphorus has 5 valence electrons, just like nitrogen, arsenic, antimony, bismuth, muscovium. That's an radioactive one. So just like all the rest of them in that column. So the answer is going to be 5. And I didn't do a calculation. I just looked at the periodic table and saw that number right there. So 5. Okay, so the last thing we're going to do here is writing electron configurations and something called orbital box diagrams. Let's go ahead and take a look. And I told you this was a little longer. I kind of put this all on the same video simply because it's really all connected. So I always like to start by showing you what an electron configuration is before I teach you how to write them. So here is a picture of what an electron configuration is. So if you just read along with me here, an electron configuration is used to describe where the electrons are. That's why we've had to go through this whole thing. And so here it is for nitrogen. And so here it's the electron configurations, and how we say it is 1s2, 2s2, 2p3. So that's how we say it, and I'm going to show you how we'll get it. I just want to break it down right now. Notice there are no commas between each thing. So the first numbers here, the 1s and those big 2s, those are the energy levels. Okay, that tells us what energy level we're in. Then I have the letters. There's S, S, and P in this particular one. Those are our sublevels. Remember, sublevels can be S, P, D, or F. So the first number tells us what energy level we're in, which will be 1, 2, 3, 4, 5, 6. Then the letter tells us the sublevels. So notice they don't tell us specific orbitals in this particular thing. We do know that any S sublevel has 1 orbital, P has 3, D would have 5. We do know that. That still holds true. Then the last thing here are these superscripts. And the word I'm using is superscript, which means above the writing. And so there's superscripts that I did in blue here, and that's the number of electrons in each thing, in each sublevel. So in the one, if I look here, the 1s sublevel has 2 electrons. The 2s sublevel has 2 electrons. The 2p sublevel has 3 electrons. Now, you can also write the valence electrons, and I'm going to rewrite the electron configuration below it because I scribbled all over the other one. Okay. So the valence electrons, by definition, are the electrons in the outermost energy level. Well, how do I know what energy level I'm in? I look at the numbers. So these are the energy levels. So we have this in energy level 1, and these two things are both in energy level 2. And the valence electrons are whatever is in the highest energy level. So all of this is in the highest energy level. So if I had to write the electron configuration for the valence electrons, it would just be writing the configuration of what's in the highest level. Now, how many electrons are in that highest level? So maybe the question is just how many valence electrons are in this electron configuration. Well, the number of valence electrons is determined by the superscripts. So in the highest level, it would be 2 plus 3 on this example. So we have 5 valence electrons represented in this configuration. Now, I want to show you how to write electron configurations using the periodic table. We have to first think of a few things. There's a few principles. One's called the Aufbau principle, which just simply means that electrons will fill from the lowest energy to the highest energy. Okay, and we're going to use the periodic table, and it is a map for electron configurations, and it does this for us. So we will know how to fill it. And then each orbital can only hold 2 electrons, which I've already mentioned before. So those are 2 things we keep in mind. Now, and let me erase all the writing I've already done on here with an eraser. There we go. Okay. Now, this periodic table can be found in Canvas. I also often bring them to class so that you can have them to work on. And this is one that I have labeled up to help you get the idea about how to use the periodic table to do electron configurations. On the exam, you will get this periodic table, but not with it labeled for electron configurations. So once you get the periodic table, you can write whatever you want on it, but it will not be labeled like this. So let's first look at the labeling, and then we're going to do several examples. So what we know is that the energy levels are related to the row that you're in. So these numbers right here, and right here, well, even here I've just extended it from the previous one. Those are the energy levels. Now, for all the tall columns, they're ones that have A's in the top of their columns. All the tall ones, the row equals the energy level. So you just count down the rows. Now, for the shorter columns down here, and they all have a B across those columns, their energy level is 1 less than the row you're in. So, like for example, in row 4, this energy level is actually starting here at 3. Now notice, once you get back into the tall columns, it goes back to being in row 4. Now, we rarely go down. Maybe an extra credit question might have you go down there. But in the bottom of the periodic table, these are taken out of this little spot here, and they're actually 2 less than the row that they're in. So we can use the periodic table and remembering those things to get all the energy levels. Then we divide each block, we divide the periodic table into blocks, and that makes up our sublevels. Now, I didn't make up the blocks. This is just how it works. So remember, we have 4 sublevels, S, P, D, and F. The S are in the first 2 columns. And that does include helium. It's just kind of on the other side of the periodic table, but it would fit. So any element within there, any box within that is in an S sublevel. The P's are over here. So it's this side. Anything within that is a P. The D's are this bridge, this middle part. Those are the D's. And then at the very bottom are the F's. So we account for all the sublevels. Now, thinking about electron configurations, we had to know the energy level, we had to know the sublevel, and then we had to know how many electrons are present. To do that, we count boxes. Okay, so each box on the periodic table, well, we look here and it has the element symbols, yes, but each box also represents the addition of one more electron. Right? Hydrogen has 1 electron, helium has 2, lithium has 3, beryllium has 4. So every time we move a box, we're actually adding an electron. So we use the boxes to count our electrons. So let's try to do nitrogen, which is one that that we did on the previous slide. And let's see how we use the periodic table to get this. Now, I know for some of you, you'll just say, aha, and you'll see it. Others of you, you'll have to practice a little more. Now, this is not the only way to do electron configurations. There's some way where you draw things down on a paper and go back and forth and back and forth. I don't know what that method's called. I really encourage you to learn it this way, especially if you're taking more chemistry, because the amount of information that you can get just by looking at the periodic table is so helpful. So if you can look at the periodic table and know something about the electron configuration, it's very helpful for you instead of having to worry about going back and forth on the chart, which I didn't even show you the chart because I don't do it that way. All right, so let's go, and I'm going to pick nitrogen. So because we're going to do the one I did here. So what we do is we'd find nitrogen. Do you see nitrogen? Whoops, I don't want it to go all the way blank. Okay, so I'll just kind of do this. There's nitrogen, N. Okay, and then we are going to count. So what I do, I start here. And I say, okay, so I say, here's my energy level. So energy level 1, so I write a 1. And when I come into the periodic table, I'm in the S sublevel, so I write an S. Because anything in those first 2 rows are S. And then I count. In the S's, I'm going to put 1 box, 2 boxes. So the first row of the periodic table is in electron configurations 1s2. And the truth is every single element except hydrogen starts 1s2 because that's the first row. Doesn't matter what element, it's 1s2. So now I would have gotten to helium. And if I stopped right there, 1s2 is the electron configuration for helium, but I'm not trying to get to helium. I'm trying to get down to nitrogen. So now I go to the second row and I think, okay, I'm in a new energy level. So I write down I'm in second level 1. Again, these 2 boxes are in an S. So I write an S and then I count 1, 2. So I put 2 that's filled with 2. And you go faster once you know how to do it. So that would be, I'm up to beryllium now. Now don't go down again. You've got, even though there's blank space, you've got to come all the way across and finish the second row before you go to the third. So then I'm still in the second energy level over here. So I write a 2 again. But now I'm in the P sublevel. So I write a P and then I count 1, 2, 3. And there you go. That's how I got it from the previous page. So, and then I also want to say, like we see there's our valence. The valence electrons are whatever's in the period your element's in. So there we got that. You see it matches. It's 5 valence electrons. So some of the ideas start coming together. Now, what I'd like to do is show you one more valence electron on this, electron configuration on this video. And then I think I'm going to stop this video and I will make a specific electron configuration video where I just go over some examples. That way this just doesn't keep dragging on forever. So let's do one more. And then I'll pause this and you can, I will have then also posted one that just has examples of electron configurations on it. And we'll go deeper into the periodic table. So let's say I'll do another one. I'm going to, this time, let's do, why don't we do let me go here. Let's do magnesium, which is right here. So it's going to, I'm going to not use red this time. I'm sorry, it's getting so messy. When I do my example one, I'll have several periodic tables. So again, I'm going to start here. If I'm going to magnesium, you start up here. And so that's a 1. And you're going into the S's. So you put S. This is magnesium. Then you count 1, 2. So do you see how it overlaps? Like it's a pattern. So it's not like you're doing something new every time. And there are shortcuts for ones that are way down in the periodic table. I'll do examples for that on the video that I do for just practicing electron configurations. So 1s2 gets me to helium, and then I'm trying to get down to here to magnesium. So I have to go to the second row. So I say 2. I'm still in the S's. And then I count 1, 2. Notice so far it looks just like nitrogen. It's not a coincidence. I go across. I'm in the 2 P's. But this time I'm not going to stop at 3. I've got to go all the way across. So it's going to be 6. That will get me to neon. Okay. I'm still not done. Now I have to go to the third row. So I write 3. I go in the S's. The first 2 columns are the S's. And then I count 1, 2. And so that's magnesium. I stop now because I'm at magnesium. And then if I wanted to do the valence electrons, so in this example, I have energy level 1, energy level 2, and energy level 3. So it's 3s2 is the valence. And that's 2 electrons. And if you look for magnesium, it's in group 2A. So we knew it should have 2 valence electrons. So I'm going to stop this video now. And I am going, you will be able to find just a practice electron configuration video if you want to see some more, see an orbital box diagram, see abbreviations. I'll put that in a separate video. Well, if you got to the end of this, I'm so proud of you because quantum theory is a lot. So I'm proud of you.